Thank you everybody for coming this evening, and welcome to you all, staff, students and guests, to our annual Andrew and Kathleen Booth Memorial Lecture here at Birkbeck. I'm Jeff Walters. For those of you that don't know me, I'm Dean of the School of Business, Economics and Informatics. It's my pleasure to welcome you all to this evening's lecture. A special welcome also to our guest, Professor Marina Jirotka, Professor of Human-Centred Computing in the Department of Computer Science at the University of Oxford. My colleague George Roussos, Head of Computer Science, will introduce Marina shortly, but before he does, I just want to say a few short words to introduce this lecture. We hold the annual the Booth Memorial Lecture on an annual basis. We have been doing for around 10 years now. As a bit of background to Andrew Booth and Kathleen Booth, they were both based at Birkbeck. Andrew was part of the crystallography team at Birkbeck, joining in 1945, a year after he gained his PhD at Birmingham. In 1946, Kathleen, then Britten, joined Birkbeck and became an extremely influential partnership, both professionally, with Andrew apparently building the computers and Kathleen responsible for the programming, but also personally, with the two of them getting married in 1950, the same year that Kathleen gained her PhD in applied mathematics. Prior to this, however, in 1947, both Andrew and Kathleen undertook a 6-month US tour based at Princeton, where they worked with John von Neumann and where they designed the original automatic relay calculator. Now, apologies for somebody who's not a computer scientist, this is all new to me. Soon after, the ARC2 was redesigned as an entirely electronic machine, which was called the Simple Electronic Computer. Following on from this, in 1952, their best-known machine, the all-purpose electronic computer, was designed here in Birkbeck's computational laboratory. So this period, you can see, was clearly a very dynamic, innovative period, an exciting one, in which the collaboration between Andrew and Kathleen and many other scholars was extremely important in shaping the direction and development of computer science as a discipline. In addition to the all-purpose electronic computer, Andrew and Kathleen were both involved in research on machine translation, on thin film storage technology for digital storage and magnetic drum and disk storage, as well as inspiring many bright minds and supporting PhD students. Their pioneering work and the recognition of the need to create taught courses in the discipline led to the establishment of a Department of Numerical Automation in 1957, and the publication of the first teaching materials on modern numerical analysis, programming and computer design, such as the landmark book Programming for an Automatic Digital Calculator by Kathleen Booth in 1958. Now, there is debate as to whether this was the first department established to teach computing in a UK university. Elsewhere, courses were still taught in computer laboratories, but it's fair to say that it was one of the first, if not the first, departments in the UK, and has grown to become our Department of Computer Science and Informatics, a leading research department in the UK. I know that colleagues in the department are immensely proud of the early beginnings of the department. Not everyone has the opportunity to work in a place with such an illustrious history, with colleagues such as Andrew and Kathleen Booth, who are so influential in their work. My colleagues in the department today continue to produce world-leading research in algorithms, data science, knowledge representation and verification that informs our teaching and, importantly, has a demonstrable impact on practice to address evolving organisational, technological and economic challenges within society. This commitment to the practical application of computer science technology raises questions regarding the governance of the digital economy. And this, I know, are questions that our guest speaker this evening will discuss. So I want to thank Professor Jirotka for giving up her time this evening to present to us all, and I want to welcome you all to this evening's memorial lecture. And I'll now pass you over to my colleague, Professor George Roussos, Head of the Department of Computer Science and Informatics, who will introduce Marina. So thank you very much, and I hope you all have an enjoyable evening.
Thank you, Jeff, and welcome to all the friends of the department to this year's Booth Memorial Lecture. Before introducing Marina, actually, I would like to also add to what Jeff said, that this year marks the 100th birthday of Kathleen Booth, one of our two founders. And after the talk by Marina, we will have a short video with a message from Kathleen. recorded with support from our departmental historian, who is at the very back of the room, Roger Johnson. So thank you, Roger, for that. And we will have a cake and an opportunity to wish her a happy birthday afterwards. So I'm sure everybody's will be looking forward to the cake at the end. But before that, it's my pleasure to introduce Marina Jirotka, the Professor of Human-Centered Computing at the University of Oxford, Director of the Responsible Technology Institute, a governing body fellow at St. Cross College, and also a board member of the Society for Computers and the Law. Professor Jirotka holds a BSc in Psychology and Social Anthropology, a Master's in Computing and Artificial Intelligence, and a doctorate in Computer Science. And her thesis title was An Investigation into Contextual Approaches to Requirements Capture. Throughout her career, she has become concerned with bringing a richer comprehension of socially organized work practices and interaction into the process of engineering technological systems. Her more recent work focuses on how new developments in machine learning and AI can be shaped to respect human agency, ensuring accountability of systems and the digital rights of individuals and communities. Today, Professor Jirotka will discuss responsible robotics, in particular her current work on merging social, legal, and technical responses in its development of the ethical black box, which was a new concept to me. So without further ado, I welcome Professor Jirotka for here.
Thank you, George. Thank you for the introduction. And thank you so much for actually inviting me to be here. It's a huge honour, particularly as we've already said, this is the year of Kathleen's 100th birthday. And as has probably been said, or as you know, her work with Andrew has been so influential and has laid the foundations for what has become computer science. And these foundations underpin how we develop software, how we can build more intelligent agents, and how computers are now really ubiquitous, that they support our everyday lives. And it's on this latter, wider issue, this sort of aspect of how computers are now ubiquitous in our everyday life, that I'm going to focus my talk today. It's a particularly exciting time for those of us involved in this area. In the last few decades, technology has become ever more powerful, allowing us to meet our future grand challenges, but at the same time, the computers have become so embedded into Western daily lives that we now just take them for granted. I'm not sure if even the most optimistic predictions of the 1940s and 50s could actually have envisioned what we have today. As you may know, the initial digital computer available in the US marketplace, UNIVAC, measured 14 feet by 7 feet by 9 feet, the size of a small bedroom. At the time, social observers actually predicted that by the year 2000, perhaps 50 of these huge, expensive machines would be in use. It was thought that only governments or affluent nations or major corporations and well-funded scientific organizations would actually be able to afford such computers. And while there were the corresponding fears of the kinds of control that would be over these, who will control these systems, people just didn't really seem to kind of anticipate at all the fact that the systems themselves might get smaller and might become more ubiquitous. So I'm actually going to look at this question of anticipation, of anticipating what might go wrong in the daily use of a mundane type of technology. And I'm going to start to try and unpack where responsibilities might lie for tackling potential harmful outcomes of technological innovation. The reason I'm doing this is because the questions of responsibility in the past, they're often driven by economic considerations, but actually these issues run much deeper and they're implicated in a wider reshaping of institutional, cultural and democratic responses to governing technology. How to divide responsibilities in the digital economy between developers, civic authorities, users of technology and automated systems, still represents a set of very unsolved problems. So the question, that kind of question, has been the focus of my 5-year EPSRC established career fellowship called RoboTIPS, or Responsible Robotics for the Digital Economy. And the novelty of the work actually lies in looking at responsibility as a focal topic within the UK's digital economy programme. We've been exploring how to embed a culture of responsible innovation, or what I'll call RI from now on, where responsibility in this context is much less about individual accountability and liability, and much more about collective care and responsiveness. We're drawing on recent research in RI to try to shape responsibility as a practical accomplishment, and we're developing new models and new approaches for how responsibilities can effectively be distributed between people, institutions, and computational agents. Underlying all my talk then, and underlying all my research, is a commitment to responsible innovation. So what I'll do first of all is introduce responsible innovation as a response to ethical and societal concerns about technology, and I'll discuss that in relation to ethics and standards for robotics. I'll then report on a case study on robot accident investigations as a kind of spotlight example of RI in practice. I'll then discuss the broader landscape of responsible innovation and some of our recent activities in the Responsible Technology Institute. But just before that, I'll ask the question here, why focus on responsibility? And so to set the scene a little bit, here are some brief reminders of some of the recent concerns that we've seen in the press as a result of contemporary disruptive technologies. The unanticipated consequences that can damage people's life choices and businesses, the potential harms to children and young people, sustainability issues, and the environmental impact of technology's vast carbon footprint. We've all seen headlines like these and many other besides. Many researchers say that these instances actually demonstrate that often questions of responsibility and accountability have been ignored in the design and development of technologies. But every new technology raises questions as it becomes embedded in society. Questions like, who benefits? What are the risks? What if we're wrong? What are the alternatives? Who decides? Who's in control? And who's responsible? We know that we can't predict the future impacts of research with any certainty. Attempting to control and prevent can leave us stuck with the status quo. But doing nothing means that control of future directions might actually be in the hands of whoever is strongest in the innovation space. So what can we do? An RI approach suggests that rather than attempt to control based on prediction, we can think much more positively and much more creatively if we anticipate the shape of possible outcomes. We can see the outline of the future space, even if we can't yet predict in detail what it contains. Anticipation is actually different from superficially similar concepts like prediction or foresight, because it makes no claims on an actual near-distant future. And unlike prudence or providence, it doesn't simply ask us for vigilance against dangers as they appear. It's related to this idea of capacity. We don't know what the future holds, but we can develop a capacity to be ready for it. We don't know how or when the capacities we've developed will be needed, but we do know that we'll be better prepared to meet the future. In this way, rather than focusing any responsibilities on whether outcomes of research are good or bad according to the balance of risks and benefits, RI is actually aiming for science and society to work together. So I want to kind of illustrate what this might mean by taking a moment to look at a particular example of the case of genetically modified crops in Europe, or GM crops, the lessons of which are highly relevant to us given the focus on corporate interests, academic research, and the trust relationship between the public and scientists. And it's actually highly relevant given the resonances with much more recent debates given our recent pandemic. And it may also show us how not to do RI. So there were a very complex set of issues behind the case of GM crops and how GM crops unfolded that you may actually be familiar with, but I'm going to do a very light summary here. And this is really to illustrate how RI came about and the context of RI in general. In the mid-1990s, the introduction of GM foods triggered a public backlash about GM crops and the biosciences more generally. The cause of the controversy has been attributed to a number of issues relating to public trust in regulatory issues, scientists, and industry. A large multinational company tried to push a new technology, GM soya, onto the European market. The push produced a backlash, and civil society organisations, which had previously not been too concerned about GM organisms, suddenly took notice. The result was a bitter fight between a few large companies on one side and increasingly vocal civil society organisations on the other. The public became increasingly suspicious of GMs in general, and the result was a more or less complete ban on GM crops across Europe. At first glance, this might seem like a classic example of technology push, and we might see how this might be unlikely to work, but this isn't the point that I want to make. A more fundamental problem was the official European government and company responses to the situation, and they responded to specific identified risks in a piecemeal fashion. They were trying to allay public fears by educating and reassuring them rather than by listening. Regulators discussed the issues almost exclusively as issues of risk to environment and public health. They failed to address people's fears that unintended effects may be unpredictable and therefore unknown to science. Neither did they address the potentially transformative impact on societal structures, which then severely eroded public trust in these institutions. By not taking account of what was driving public concerns, the motives of those developing the regulatory frameworks seemed very suspect. The initial reaction to the public response to GM was to actually dismiss their fears as irrational, and regulators and scientists tried to regain the public trust by educating them with facts and information. Predictably, the more the company tried to reassure the public, the more the public became suspicious. But the basic failure was a failure to try to anticipate and reflect on the wider risks and consequences of GM crops. Firstly, regulations were exclusively focused on safety aspects where the broader environmental, social, and agricultural contexts were not reflected on. And secondly, there was a complete failure to engage openly with stakeholders, so that methods of one-way information provision were wholly inadequate for the task of addressing the human tensions and the social dynamics. By the second half of the 1990s, this strategy proved to be highly ineffective, and the EU moved to more participatory strategies. The main driver for this was the belief that to ensure societally accountable development of technologies, there must be larger public involvement in debates and decisions. And that research must actually focus on what Morten Østergaard, former Minister of Science in Denmark, said: we need ambition at a policy level to support the best science for the world and not just the best science in the world. So it was against this backdrop that interest in responsible innovation grew, where we were to ask ourselves the question, but what kind of society do we actually want, and how can technology help us get there? So the RI initiatives across policy, academia, and legislation emerged over a decade ago. They began with an aim to try and identify and address uncertainties and risks associated with novel areas of research, beginning with nanotechnology, moving to the environmental and health sciences, including geoengineering and synthetic biology. The scope of RI has recently since expanded to include computer science, robotics, informatics, and ICT more generally. In the EU, where a great deal of fundamental research in and for responsible innovation has been done, it was a cross-cutting theme in Horizon 2020. In the UK, the Engineering and Physical Sciences Research Council has made a commitment to RI across its ICT portfolio of research grants. So what is it responding to? What is RI actually responding to? It's responding to the fact that many of the problems that we face are actually a legacy of our failure to attend to potential negative impacts of innovations in the past. Increasingly now, we see the public and media expressing concerns over these potential negative consequences of innovation, in contexts actually where technology is becoming ever more potent. nanotechnology that seeks to manipulate matter at a fundamental level, synthetic biology that aims to create new forms of life, AI and increasing automation risks de-skilling and disenfranchising the most vulnerable in our society, transhumanism that's trying to transform the human condition by developing technologies to enhance human intellect and physiology with the associated fears of meddling with nature, and pervasive ICT that, while appearing to improve human connection, uses surveillance technologies potentially to our detriment. So there are some practical actions and a framework which are suggested as a way to carry RI forward. And the core aim is actually to try and involve all relevant stakeholders, including the public, and to encourage those stakeholders to try to anticipate and reflect on the consequences of scientific and technological innovation. And this is in instances of a high degree of uncertainty or ambiguity about what the future pathways of innovation might be. It's been defined as doing science and innovation with society and for society, including the involvement of society very upstream in the process of research and innovation. And that means that's at the point of where an innovation is actually first conceived. And the idea to do that is because you want to align your outcomes with the values of society. It consists of a set of processes for ensuring that innovation benefits our world. It draws on anticipatory governance, where both potential positive and negative consequences, intended and unintended consequences of an innovation, can be anticipated and brought to developers' attention in order to try to influence the trajectory of a particular innovation. So although there's a number of frameworks for RI, several of them are built on these 6 pillars. These are ethics, open access, governance, gender equality, science communication, and public engagement. And in the UK, building on Richard Owen and Jack Stilgoe's work in geoengineering, the EPSRC harmonised these principles into something called the Area Framework, that I'm sure you all must be familiar with by now. And so what does the Area Framework actually do? That framework breaks down how to consider doing responsible innovation into a very broad series of activities. The first dimension is to anticipate, describing and analysing the impacts, good and bad, intended and unintended, that might arise from a new technology. This isn't about trying to predict, as I said before, but within the bounds of plausibility, to be as imaginative as possible, opening up the space for discussion, even if there's no concrete evidence to envision future consequences. So rather than attempting to control the future or passively waiting for the next stage of development, anticipation actively opens up that design space, creatively looking for or underexplored pathways and digging into their possible implications. Secondly, RI is reflective, thinking carefully about the overall purposes and motivations, identifying what is known, what is not known, and not being afraid to admit that there are associated uncertainties, risks, areas of ignorance, assumptions, questions, and dilemmas. Being reflective in practice is trying to make visible the often hidden dominant assumptions and values, holding up a mirror to them, and looking at your own assumptions as a developer as well. It's pausing to reflect. Everything in tech is always so fast. Here we're trying to recognise the limits of your own knowledge and being aware of the broader, much broader, systemic context of the problem that's actually being addressed. Thirdly, RI engages. It opens up visions, the purposes, questions, and dilemmas to inclusive and wide-ranging deliberation through formal and informal processes of dialogue, engagement, and debate. Engagement will give us different perspectives, and it will certainly give us new ideas. So that finally, it actually tries to act to influence the direction and the trajectory of a particular research and innovation process itself. The core idea here is responsiveness as an aspect of responsibility. This might involve formal mechanisms of participation and anticipatory governance, or whatever helps to make sure that science and society are mutually responsive to each other. And it's not a once and for all, but an ongoing process, looking at how new technologies meld with old, how people adapt, and how we as researchers and innovators adapt to emerging knowledge of technology use in the world. The framework as it's set out here tries to be as clear and practical as possible, bearing in mind that research and innovation is often unpredictable and unclear. And it's not a linear progression from one dimension to the next, rather it's iterative and flexible. Being responsive includes being reflective and engaging. Often reflection involves elements of anticipation. Engagement can and should throw up new issues, which will then require further reflection. So in this way, RI is not about closing down options, but rather it's a space for creativity, for confidence, and for serendipity. It's not predefining what are and are not the right impacts for research, but it's providing us with a framework which can help us to decide what those impacts might be and how we might realise them. But it's not a silver bullet, and there are many challenges that remain thinking about how to embed responsibility into the processes of technological design and development. And I've listed quite a few here. And in addition to that, the pace of innovation continues to grow very quickly. The tension between profit and responsibility also grows stronger. And users are increasingly feeling ill at ease in the digital economy, with values of trust, identity, privacy, and security potentially undermined. In relation to all of that, researchers and developers who are working in the UK digital economy are experiencing a huge amount of uncertainty about where responsibilities lie for tackling harmful outcomes of technological innovation. There are so many controversies about, for example, who should monitor the actions of algorithms or remedy unfairness and bias in machine learning. Whose responsibility is it to do that? And it's this that has formed the focus for my fellowship in responsible robotics, or RoboTIPS. And RoboTIPS itself is a collaboration between the University of Oxford and Bristol Robotics Lab. And in our investigations, we're focusing on social robots as a motivating example. Broadly speaking, social robots are those which interact with humans on a daily basis. For example, autonomous vehicles, companion robots, toy robots, and so on. In our work, we've defined responsible robotics as the application of responsible innovation in the design, manufacture, operation, repair, and end-of-life recycling of robots that seeks the most benefits to individuals and society and the least harm to the environment. As we've actually noted, that RI has engaged less in the past with the environmental footprint of ICT. But why should we focus on RI when we have all these ethical principles and guidelines to help inform design and a rich history of reflecting on the ethics of technologies? It's interesting to note that an informal survey that we did at the end of 2017 discovered that a total of 10 different sets of ethical principles for robotics and AI had been proposed by December 2017, 7 of which had been actually appeared in that year. And there are many more now too. According to some recent counts, there are more than 100 set of guidelines. Now, there's a good deal of commonality across those principles, but several of them stress that the responsibility for things going wrong in the robot must lie with designers. And we think that decisions like that need a far more nuanced approach, a far more nuanced form of governance when considering the potential use and abuse of these technologies in context. Okay. Now, ethics and standards both fit in within this wider framework of responsible innovation. RI can provide a scaffold for ethics and standards, as we see in this slide. Responsible innovation typically requires that research is conducted ethically, so ethical governance connects with RI generally. But RI also connects directly with ethics through principles of, for instance, public engagement, open science, and inclusivity. A further key principle of RI is the ability to systematically and transparently measure and compare system capabilities, typically with standardized tests or benchmarks. Standards and ethical guidelines, however, are not practice. So to explore this more, we really wanted to understand what developers think about RI and to try to begin to embed practices of responsibility into the innovation of digital economy technologies. Now, you might ask yourself, well, aren't all developers responsible anyway? It would be nice if they were, but actually they don't think about the future consequences of their innovations, and they do not orient to notions of responsibility in the way that they design. So these are the kinds of things that we were trying to open up. So we're trying really in social robots to draw on the expertise of a Bristol robotics lab to examine how to develop accountable and explainable systems relevant to a range of stakeholders, particularly when the technology seems to go wrong, in order to develop more trustworthy systems. Trustworthy systems is a big mantra at the moment. So how is it that we come to trust any kind of tech? One of the reasons we trust airliners, until recently perhaps, is that we know that they're part of a highly regulated industry with a strong safety record. The reason commercial aircraft are so safe is not just good design, it's also tough safety certification processes, and when things go wrong, a robust social process of air accident investigation. We suggest that acceptance of air travel, despite its catastrophes, is in part bound up with aviation governance, which has cultural and symbolic importance as well as practical outcome. A crucial aspect of the former is rendering the tragedy of a disaster comprehensible through the processes of investigation and reconstruction. So, in relation to all of that, the following a discussion really that Alan Winfield, who is the brilliant professor of robot ethics at Bristol, and we had this discussion at one of EPSRC's robot ethics workshops. We decided then to look at social robots through the lens of RI and try and look at what happens when things go wrong. So let me start with a scenario. Imagine that your elderly mother, Rose, has an assisted living robot to help her live at home independently. The robot's able to fetch her drinks, remind her to take her medicine, and help her to keep in touch with her family. Then one afternoon, you get a call from a neighbour who's called round and sees Rose collapsed on the floor. When the paramedics arrive, they find Rose's robot wandering around, apparently aimlessly. Now, one of its functions is to actually call for help if your mother stops moving, but it seems that the robot failed to do this. Fortunately, in this scenario, Rose recovers, but not surprisingly, you might want to know what happened. Did the robot cause the accident? Or maybe it didn't, but did it make matters worse? And why did it fail to raise the alarm? Now, although this is a fictional scenario, it could happen today. If it did, you would be totally reliant on the goodwill of the robot manufacturer to discover what went wrong. And it's entirely possible that the robot and the company are not equipped with the tools and processes to actually facilitate any kind of investigation. So it may surprise you that right now there are no established processes for robot accident investigation. Now, of course, accidents do happen, and that's just as true for robots as any other machinery. And finding statistics is actually quite tough. But this web page from the US Department of Labor shows serious accidents with industrial robots in the US since the 1980s. Now, driverless car fatalities, of course, make the headlines at the moment. There have been 5 that we know about since 2016. And we have almost no data on accidents in human-robot interaction. That is for robots that are designed to interact daily with humans. Here is one, a security robot that just happened to be reported. But a responsible roboticist must be interested in all accidents, whether serious or not. We should also be very interested in near misses. Near misses are taken very seriously in aviation, and there is very good evidence that reporting near misses improves safety. So in our work, firstly, we've considered a technology that might be needed to support accident investigation. And in a paper published in 2017, Alan Winfield and I argued the case for an ethical black box, or an EBB. Our proposition is very simple, that all robots and some AIs should be equipped with a standard device which continuously records a time-stamped log of an internal state of the system, makes its key decisions and sampled input and sensor data. In effect, it's the robot equivalent of an aircraft flight recorder. Without such a device, finding out what the robot was doing and why in the moments leading up to an accident is more or less impossible. So currently we've created several model EBBs for different robots and robot operating systems, which robot developers can actually copy or customize for their own robots. We've also started considering a standard for the EBB, We already have experience in the team of drafting standards for both the British Standards Institute and the IEEE Standards Association, and we've used that experience to draft what we call an open standard for the EBB. And an open standard is simply a standard which is made freely available to everyone. And our aim is that others will actually develop EBBs which comply with that standard, and that will make the work of robot accident investigation much easier. However, accident investigations are above all a social process of reconstruction that need to be perceived as impartial and robust, and which may serve as a form of closure so that aviation doesn't acquire an enduring taint in the public's consciousness. And we anticipate very similar roles for investigations with robot accidents. Crucially, it's not the black box on its own that forms the safety mechanism. It's its inclusion in a social process of accident-incident investigation. So an investigation will draw on EBB information and information from human witnesses and experts to determine the reason for an accident and lessons to be learnt from it. So alongside the technical parameters of what to record in the EBB, we also have to think about how the interpretation of those data fits into the process of an investigation. So we're designing and running 3 staged mock accidents, each covering a different application domain. And we believe that this is the first time such an activity has actually been done. And we're also very lucky to have a real accident investigator helping us on the team. The 3 applications that we're looking at are assistive living robots, educational toy robots, and bionic prosthetics. And in these scenarios, we're using real robots and using human volunteers to act in 3 roles as the subjects of the accident, witnesses to the accident, and as members of accident investigations. What we're trying to do is develop and demonstrate both technologies and processes and ultimately policy recommendations for robot accident investigation. And the whole project is conducted within the framework of responsible innovation. And in effect, it will be a case study for responsible robotics. So we were delayed somewhat by the pandemic, I have to say. The robotics lab was closed for 2 years. We couldn't get to any robots, much less have people come in and do mock accidents. But on April the 7th this year, we ran the first pilot of our first mock accident investigation, the one that involves the social robot in a care home. The goal of the pilot was to test the scenario that will be used for the official one in July 2022, in which we're planning to involve the real accident investigators. So in the picture, you can see a few researchers at the Bristol Robotics Lab playing the mock accident scenario in the kitchen of the assisted living home there. On the left, you can see the neighbour discovering Ross, he's a male, so it's not Rose, and injured on the floor. On the right is a paramedic attending to Ross while the Pepper robot is moving around somewhat aimlessly. In this slide, you can actually see the investigators, 2 colleagues from the Institute, who had no prior knowledge of the circumstance of the accident, and they had to rely on 1, inspecting the robot at the scene of the accident, 2, the data from the EBB, and 3, testimonies from Ross, the neighbour, the paramedic, the cleaner, and the facility manager. In the end, the actual investigation went extremely well. The EBB, alongside the consideration of the not always reliable witness testimony, enabled our investigators to correctly deduce the role that the robot played in this particular accident. But again here I'm going to say, well, why do we need robot accident investigation? You might be thinking that's rather a lot for a bit of a robot. Well, although robot accidents are thankfully rare, the scope for accidents in second wave social robots is much greater than first wave industrial robots, and here are 3 reasons. First wave industrial robots operate behind safety cages, whereas social robots are designed to be amongst us, up close and personal. It is this close proximity that presents the greatest risk. Second, industrial robots typically operate in an environment optimized for them and not humans. Social robots do not. The unpredictability of a human environment is far more likely to cause social robots to fail. And third, the range of serious harms that can arise from social robots is much greater than those associated with industrial robots because they actually also include ethical harms. So, If we return then to our fictional scenario, how would we expect the actual investigation to play out? First, the accident investigation team collect testimony from witnesses, including Rose herself. And the key points from the witness testimony are: the neighbour finds Rose on the floor in the kitchen and immediately calls the paramedic. The paramedic attends to Rose, but also reports seeing the robot in the living room. He also notices that Rose is not wearing her fall bracelet. The cleaner reports that she cleaned, as usual, she cleaned the robot using disinfectant as instructed. Rose says that after recovering, she wanted something from a kitchen cupboard and she climbed onto a chair to reach that item and she fell. She also remembers calling out for help. So next, the accident investigation team examine the data from the robot's ethical black box, and they construct a very simplified timeline shown here. Interactions with Rose are shown in orange. Robot movements are shown in blue. Note that in reality, they would show the XY positions of a robot. The robot connection status to the home hub is shown in green. The robot's connection to the home hub is actually important, as this is how the robot connects with both the home's smart sensor network, including Rose's fall bracelet, and raises the alarm in case of accidents. So bringing the witness testimony together with the EBB data, the accident investigation team construct a why because graph that's shown here. Why because analysis is a very well-known technique for establishing causal links between events, unevents, that is things that should have happened and didn't, states and processes. The root causes are at the bottom of the graph and the resulting accident at the top. So in the analysis of Rose's fall, we can see that there were actually two accidents. Accident 1 was Rose's fall, accident 2 was the robot's failure to raise the alarm. So the why because graph for Rose's accident is actually two linked subgraphs as shown here. The key findings of the accident investigation are that accident 1, Rose's fall, was caused by her unwisely climbing onto a chair, and accident 2, the robot's failure to raise the alarm, was caused by a combination of sensor and connection failures. And the investigations team recommendations are: 1, equip the robot with a backup communication system in case the Wi-Fi fails. 2, equip the home hub with the ability to send an emergency call directly via a landline, for instance, when the fall bracelet is triggered, so that a particular alarm is not routed via the robot. 3, improve the sensitivity of the robot's microphone to increase their range so they can hear when Rose is crying out. And add a new function to the robot so that it reminds Rose to put on her fall brace every day. And finally, advise the cleaner not to use disinfectant on the robot because this can interfere with its sensors. From the social process of accident investigation, I don't think we can actually underplay the importance of looking at the form of EBB explanation in the social context in which it's actually going to be used, not least so that we can have a model of what that social context is actually going to be. We need to think about how an investigation should be structured in order to give trusted outcomes. What are the important roles and evidence that need to be presented? What sorts of social dynamics and power relations exist? And how are these mediated through the processes of the investigation and through the technology that's both investigating and using to help with the investigation? We need to think about how to gather appropriate data for the EBB and how to design the capabilities. Most importantly, how can it actually explain its behaviour, and how can these explanations be made relevant for a range of participants? Eventually, we'd like to allow the robot user in care homes or in potentially in accident investigations to be able to actually ask the robot, why did you just do that? Or even in the future to ask, what would you do if? And for the robot to give simple explanations that are shaped and useful for the setting. So our team is actually working with a whole range of business designers and partners to co-develop the requirements for the EBB in each of the study domains, and at the same time looking and trying to understand how they're orienting to notions of responsibility in their own practices. One of the clear areas of concern for them, for the developers, was the recording of the EBB for social robots, and that was privacy. this is actually really quite interesting. The increase in the use of social robots in almost all cases leads to an increase in recording, with the exception being of very simple robots. Robots are attractive because of what they are capable of doing: navigating a room, having a conversation, calming a child. Yet their differentiation from more classical electronics is exactly what makes them attractive: the fact that they can collect and act on information. And this can be done through a variety of ways: video, audio, or sensory data. While sensory data is the most privacy-friendly, as it's least likely to actually reveal any personal data, it provides the least information for the robot as well. Video and audio recordings are intended to take in information about their surroundings in order to interact with it, but it actually increases surveillance in the spaces that they actually inhabit, and even if surveillance isn't their primary purpose. Sensitive information is collected as matter-of-factly as anything else, and all the more likely as robots extend into individual homes. With this expansion into homes comes the erosion or invasion of that private space. Most people have ideas about where they're likely or unlikely to be overheard and the appropriateness of topics in that space. There's an understanding, albeit imperfect, that you can rely on the discretion or dissemination of the space and the people that inhabit that space with you. There is an advancement of this to include digital recordings, but it requires an understanding and an awareness of where and how that recording might take place. While a person might balk at their host setting up a video camera or a tripod during dinner, they're far less likely to object to or even notice an automated vacuum cleaner. This sort of contextual area-based privacy has started to be eroded quite a while ago with things like virtual assistants. Not only are they vulnerable to security attacks, but they're also listening beyond what many of their users would assume. Whatever their wake word is, they're listening. Robots take this step further. Not only do robots have the potential to be in a variety of spaces, but also they can move between them, entering and exiting situations and conversations unannounced. The erosion of privacy can be as basic as a back garden or as intimate as a bedroom or bathroom, and it applies to any inhabitants or visitors that enter into that space. The third privacy concern, of course, is access by third partners. The potential concerns around recording aren't generally based on the fact that the robot is listening or watching, but the idea that another person is or will be. And this depends on several factors: the retention periods and use of the recordings, the measures that are taken to protect them, and which parties have access either intentionally or unintentionally. Recordings might actually be used for the immediate function of the robot or to improve its use over time, potentially by investigating issues such as using the EBB. But even well-protected recordings can have audiences that are unsuspected by the user. As you know, Google admitted in 2019 that contractors could access recordings made by Google's Home Assistant. Even more seriously, Amazon's Alexa was effectively called to give evidence in a double murder case in the US as early as 2018, with a valid warrant served based on the probable cause that the Echo had picked up audio recordings during the attack. Beyond such drastic uses, the basic privacy concerns of excessive sharing and processing can lead to both chilling and conforming effects as information is shared from inside to outside the home, as people become more aware that the home is a less private space. Now, there's been a growth of different guidelines and standard settings in robotics in response to these ethical and societal concerns. All kinds of things from the British Standards Institute, BS 8611 for ethical design and application of robotics, the IEEE's recommendations practice for assessing the impact of autonomous and intelligent systems on human well-being, the European Data Protection Board's adoption of guidelines on virtual voice assistants, which includes guidance and compliance with other legislation such as GDPR. Now, while these current laws and regulations such as the UK GDPR will and do apply to recording and privacy spaces, these do not satisfactorily address the broad spectrum of our concerns. While they might establish best practice for, say, data processing by companies, breaches do still happen, and there is a significant gap between standards and enforcement. So while video and voice recording purposes should be documented and have a lawful specified reason for recording and likely explicit consent, it may be unlikely that individual users will actually connect the idea of surveillance with what is marketed to them as something very different, a toy, a care aid, or a mop. Additionally, then, some of the best practices and requirements around recording, such as informing those being recorded, don't actually address concerns such as the psychological repercussions in chilling and conforming effects. Being notified of one's recording in a corner shop or a train station is very different than being notified of being recorded in a friend's back garden, whether or not the recording is likely to be used. It is important, then, that we incorporate, normalise and build on the standards and guidelines that are built from responsible innovation in order to maximise not only the utility of our social robots, but to prioritise the preservation of human rights and dignity. One area of RoboTIPS research, then, is to try to develop a practical framework for developers to engage with in these kinds of issues. They don't often think about this when they're building these things. Considerations of how technical and socio-legal concerns can best be incorporated into human-centred practice. Privacy is just one of these elements and leads us to some serious but contextual questions of how much information is necessary for the purpose of each individual robot, how data collection can be minimised, access protected, and privacy invasion rebuffed, among other concerns such as transparency, accessibility, and accessible explanations. Privacy is not alone, however, and the societal impacts must be considered alongside the technical. The language that we use to discuss and examine innovation is important, a concern reflected in the IEEE's ontological standard for ethically driven robots and autonomous systems. Other incorporated RIA elements include primary and secondary harms, both positive and negative. What happens if a robot doesn't work perfectly? What happens if it does? Key to the concept of doing science and innovation with society and for society is engaging not only with the technology itself, its function, accuracy, bias, utility, but also its broader effects, its environmental impact, psychological effects, and even dependency. That is not to say that these deliberations are simple or straightforward, but they are necessary in shaping not only the world that we wish to see, but a world that we might wish to live in. So, in this research, we're also creating a new approach for developing requirements for these types of social robots, a trust, rights, and relation-based approach, which is going to explore the kind of networks and obligations that users inhabit in each of the study domains in order to try to understand their lived experiences better. Often, designers in human-robot interaction focus on a single user and a robot, but in many cases there are constellations of users, families, care workers, teachers, the dog, and others whose interactions with a robot and the principal user provide valuable information to add to their design. The incorporation of these social robots into these everyday contexts also problematizes our understandings of autonomy. Interactions with robots in a given scenario creates a fluidity of autonomy in which a user can have more or less control over decision-making depending on the task at hand. So we're also thinking about how human autonomy can be balanced appropriately with responsibility and thinking about ways in which it can support rather than undermine interactions. Often autonomy is thought of as an engineering concept. And increasingly, not only policymakers, but also businesses and innovators feel an increasing duty to try to engage with policies and to try and think about these social consequences for their innovations. The World Economic Forum has called for a more inclusive and agile form of governance. So we're also thinking about new forms of agile anticipatory governance. And RI proposes a new process for research and innovation governance, and it's trying to be much more adaptive, human-centered, inclusive, and produce sustainable research and innovation processes from the fundamental research through to application design and beyond. This form of governance of necessity must be an increasingly multi-stakeholder type of effort that tries to anticipate problems, taking into account wider ethical and environmental issues, and trying to create flexible and adaptive systems to deal with unintended consequences. So we're actually going to conduct a series of speculative reimaginings of different sorts of novel institutions, novel technologies, novel kinds of government as a tool for fostering an application of these issues and creative solutions among digital economy innovators, policymakers, and other stakeholders. The potential impact of the work is quite extensive. The EBB could change how we develop these products in social robotics and potentially beyond. The work proposed could lead to new opportunities for companies to design and manufacture standard black boxes for each different class of robot. It's a fundamental contention of this work that if we increase transparency of how these technologies make their decisions, and we take users' obligations and their lived experiences seriously in the design of these tools, and that we are seen to be doing so, then we may increase trust in these types of technologies. The reverse is also the case, that if a company does something societally unacceptable, as in my first example, it could have an adverse effect not only on the company, but also on the whole area of development. We still haven't solved the GM food issue. It is in the end, when things go wrong, that the responsibilities throughout the chain of creating, commissioning, and deploying social robots will actually take centre stage, albeit retrospectively. The proposed case studies really are a kind of vehicle for understanding what the chains of responsibility will look like when a harmful incident happens, and provides an unparalleled opportunity to simulate disaster in a safe way and to try to understand how to manage its consequences. So based on the kind of influence of the RoboTIPS work, we've also recently been given an award to set up a Responsible Technology Institute at Oxford and to take that work into a much more international arena. The new interdisciplinary centre tries to be an international centre of excellence on responsible technology, and we're trying to establish a creative and robust community to discuss and develop culturally nuanced approaches to responsibility and responsible innovation. The objective then is to take an international focus on how societal challenges are presented and how emerging technologies are treated. We want to unpack the complexities around understanding of responsibility and different regulatory environments. We want to try to address gaps in industry and industry-related approaches to responsible technology. We've got a number of projects already. Currently, we're looking at interrogating the climate impacts of ICT. We're developing community labs on tech futures. We're researching into trusted autonomous systems, focusing on vehicles and drones. And we're designing digital interventions to improve adolescent mental health. And we continue the work on Orbit, which provides leadership to give the to support the RI community and to provide RI services, things like training and consultancy to academics and industry innovators alike. Since we started, Orbit has trained hundreds of students now, a new generation of scientists and engineers. We've also established peer-to-peer forums for the exchange of knowledge and best practice about RI. We've launched a journal, and we just recently created a spin-out company. So where do we go from here? So at our institute, we have 3 goals. We want to serve as a hub for sharing best practice and common purpose, supporting and amplifying the networks that we're building and that we're leading on responsible development and innovation globally. We want to engage with policy and industry leaders to share the research, to find common goals, and to create coherent strategy across the whole innovation development life cycle, from the beginning of the idea to the end of the life of the technology. And we want to create a supportive platform for diverse projects founded on responsible innovation principles, ideas that actually prioritize forethought, accountability, and fairness in the development of novel technologies. We want the future of technology to be a healthy one and a creative one, but fundamentally it needs to be a responsible one that takes care of users, of the planet, and of our future. And that is the end of my talk. But before I just want to give a shout out for the wonderful people that I work with on the RoboTIPS team. And I will also tell you that I have given you some references too, if you want to check through the many things that I've actually talked about today. Thank you very much.